So we're nearing the end of the semester now, so I'm going to cover some special topics. One of the books I referenced called these advanced topics, but I actually think they're important topics. And I will give you a homework assignment out of it. It's only briefly mentioned in your book. And then next week is the last week of classes, and I will not give you homework due next week. We will have some review for the final exam, and we'll talk about that in a different video. Okay, so this video is special and advanced topics. So we're going to talk more about the header files and how that comes together, and then using multiple source code files for making larger programs, and then how to compile those all together into one executable. And so there's a couple of topics there listed that we'll talk about, but I hope what it gives you is a better viewpoint of how programs are constructed, especially larger programs. So far in this semester, we've written one program at a time. So in our one program, you have comments at the top, you have your includes, your defines, your preprocessor directives are right here, right? Preprocessor directives. You may have a function prototype up here, which is like a declaration that you have a function. Then you have your main body of your program, and then after that you have your function definitions. So this is not a declaration, this is a definition. It defines what the function does. So that's what our general program structures have been all along. But when programs get very, very large, a lot of times these definitions are moved off into a different file, and definitions for functions are also moved off into a different file. So what we want to see is the ability to have multiple source files, which helps us modularize our programming, test each part of the program independently, and then we want to be able to compile all of these together into one giant executable. So that's what the majority of this YouTube is going to be about. So large programs, if you have a really large program, you should divide it up into smaller modules. That makes sense, and then each programmer can work on a module separate from the other modules. And with that being said, the modules also become generic, and only the main calling function puts the values into the modules, for example. So you always have to have one main function. So main is a function. You have to have one main program. You can't have more than one main program, and that's the main calling function that would call all the other files that you have included in your main large program. And so you can have other source code files like function1.c, function2.c, or whatever. So anyhow, if you go for this modular approach, then you want to keep all of your definitions, like variable definitions, function prototypes, in one. And it would be nice to keep them in one module, so all the definitions are in one place, and then all of the other functions and other files can use the definitions. So we centralize these definitions into one file, and we share this file amongst the different modules, or these are source code files, right? .cs. And such a file is called a header file. And you're actually already familiar with header files because you've been using standard io.h since the beginning, since day one. And it's kind of fun to see what standard io.h does. You know by now that certain functions come from this header file, so these functions are defined in standard io file, or the standard io header file defined functions like printf and scanf, and we can actually see that. So I put some links down there, so I'm going to go ahead and show you those links because it's a little bit fun and probably informative to look at. No, you don't want to look at my email. So this is actually what is contained in the standard io.h file, and it's full of comments, it's well documented, but if you read through it, there's some includes, there's some defines, there's lots of comments. Eventually you'll find printf and scanf defined, but you'll see the function prototype there for scanf and printf or whatever functions. So this is actually a gargantuan file. to look at, and has all of the functions that printf that you have at your disposal when you include printf .h, or when you include standard.io.h, you get a bunch of functions like printing and scanning from the console, and a lot of other things too, end of file, etc. So so that's why we include standard.io.h. There are other references on the internet that are also informative. This one is from Tutorials Point, talks about the standard I/O library, C library, and then if you look at it, this page, it defines what some of these things that we've been using are, like end of file. You can go on library functions. So these are the function prototypes are defined, for example, in here. So it's like, here's your file open, what the argument should be, because that's really the function prototype that's defined in the header file. So if you go on, it's interesting to name. Here's printf, for example, tells you what it does, sends formatted output to the standard out, and you can click on it and get a little bit more information on it down here. You can see what the argument of the printf function is, but these are all defined in standard.io.h. Here's another list, this one from another website, that lists all the functions that you can get. Lists all the functions you can get from the standard.io.h header file. So these are functions that you have at your disposal. You've seen them at on our reference sheet. Here are some constants, end of file, nulls. So we've seen these. Interesting to see what makes up standard.io.h. So back one slide. But we can define our own header files. All you have to do is put a .h extension on it, and it doesn't even have to be a .h. We make it a .h to obey convention, and so that somebody who looks at it knows that a .h file is a header file. In this file, you can have declarations, function prototypes, structure definitions, symbol definitions, extern statements that we haven't talked about, and type defs that we haven't talked about, although we are going to talk about extern statements today. So when you put all these definitions in one place, you don't have to put them in all the other modules, all the other bits of source code files that you have written, and you keep them all in one centralized place. It makes sense. So I do note here in yellow that header files don't contain function definitions or initialized data. A definition is different than a declaration and a prototype. And I have here, I think I have an example. Yeah, for example, down here, this is a function definition. This is a function prototype. So function definitions, it says, do not belong in the header file. Function prototypes do. So you'd put the prototype in the header file, but you would have somewhere else some other bit of source code that would define the function itself. Sounds confusing so far, but hopefully you will see it soon and it will start to make sense. But I will say that it takes a little bit to get all of these concepts together. So definition is different than a declaration or a prototype. So header files have declarations, function prototypes. You can define a structure there, but it does not contain global data, and it does not contain function definitions. So I'm going to, I think, proceed to an example now. Here's our first example, start of the example. So any file can be included in your program, and you can include a whole bunch of files all together into one big program, but not just header files. But in my example right here, I'm including a file that I just call myfile.h. The only difference is when you write your own header files, it says that you should put them in double quotes instead of the triangle brackets, but it only has to, the only difference is really how the compiler will treat it. I will say that when I put this in the triangle brackets, it still worked, but let's obey the convention here. So what's in this include my file? We don't know yet. So this the includes are all part of the pre-processing, which we have been including in our programs for quite some time. But one of the things that the pre-processing phase does is it compiles all of these other things that your program might need, and it's ready for your program before it ever compiles the actual program. One of the reasons this is going to be nice is that you can compile your header file and not have to compile it again. And so it will save time on compiling, especially when it becomes to be very large programs. Okay, so now here's a real example. I have 3 files. One of them is, well, it's very similar. It's very similar to this little block diagram that I did here. My names are a little bit different, but there will be a name, a main program. There'll be a program that has function in it, and there'll be a program, and there are 3 separate files that will be a header file, and I want to compile these all together and make one giant program. So my names are a little bit different when I actually did the example. So I have a file here called miscellaneous.c, because I was doing miscellaneous topics, and so I named it that. But you see it has the main function in it, and it includes my header.h. And I see a little typo here. Okay, but I'll run the program for real, because I see that I don't have it says my header with lowercase. So and this is the file my header.h right here, and all it has in it, it defines what pi is, and it has a function prototype for a function called write my message. Doesn't say what write my message does, but there's a function prototype for write my message here. And then I have yet a third file, and this file is called write my message.c. I wrote it in Notepad++. And inside this file, it has the definition of what this function does. So all this function does is write a message. And then this main calling program calls that function. See right here it says write my message. It calls this function. This function exists in another file. It also says the value of pi is, and it gets what pi is. It gets pi from the header file. So let me show you. When you run this file, yeah, I fixed it when I ran it. So this is how you compile it all together into one big program. I have 3 different source codes right here: miscellaneous.c, my header.h, write my message.c, and I want to compile it all together into one large program, which I called large prog, so to pretend it was a large program. And then you have a big long compiler statement here. Looks similar to what we did before, except that we have 3 different files that we compile together to make large program, which is right here. And then I ran large program, and it did exactly what it was supposed to do. It printf'd the word running, this is my message, and the value of pi is whatever. So the program ran, and I compiled it all together and made one executable from 3 different files of source code. So one other thing about it in the header file is talk a little bit more about the header file, the actual header file. Where you put include standard IO is also important. You can include standard IO in your main calling program if you want, but you can also put it in the header file. But whatever you do, standard IO has to be compiled with part of your program before you do the first usage of it. So before I ever call printf, I must have already compiled standard IO as part of my large program. So I'll go back for a moment. In this first version, include standard IO was in the main calling program, which is fine. It worked. And then in this version, I put include standard IO in the header file, which is fine. That also works. So, but I included, since I included it as part, it's in the header file, that's okay. And when I run the program, it gets the fact that standard IO is here before it ever prints the message. So it's a little tricky, actually. Okay. So let me show you a little bit now let's go on a little bit more, one more slide. So that giant compile statement is not very pleasant to type up. And so, but it's kind of error prone and tedious to type long compile command on the command line, especially if you have a lot of files that you have to compile together. It's also problematic because if I'm doing it on the command line like that, I'm recompiling all of those source files every single time. And maybe I don't have to recompile all of those source files every single time. Maybe only one of those source files changed, and only that one needs to be recompiled, and then the giant large program gets recompiled. So there is a tool to help us do that so it won't be so problematic, and it's called the make utility. So this utility came with our GCC compiler. You downloaded it at the beginning of the semester when you downloaded Cygwin and the GCC compiler. You also were asked to put make on your computer. So it's a utility that helps us, and let me explain a little bit more what make does. Besides not having to type big long compile commands and recompile everything every single time. So make, it's a file that you, here I'll show you a make file. This is a make file. So if you look at it, you can see that that big compile command is embedded in here, but a lot of other things are happening too that I'm going to tell you about in a moment and show you why this is advantageous. So how do you make a make file? So the make file describes the steps to compiling a program, and what it does is it looks to see which sub-source files have to be updated before it can remake the large program. So this is how it saves us time, and also you don't have to type all that big long compile command again. So you have in the make file, you have dependency rules and construction rules. The dependency rule has two parts, a left side and a right side, and you have a left side colon right side. For example, my program is the ultimate executable, and then that's the left side. So this is also called the target, and then on the right side is all the things that my program depends on. So this is a dependency rule. So my program, my big program, depends on a main.c, a function1.c, a function2.c, a myheader.h. So the left side is called the target. You can have actually more than one target, but we'll stick with one target. And that's the big executable that you have to build. And the right side gives the names of the files on which the target depends, which are source files, header files, it can be data files as well. If the target is out of date with respect to the dependencies, then you have some construction rules that will follow. So your computer keeps track of when my program was last compiled, and then it keeps track of when each one of these individual dependencies were last compiled. And if one of these dependencies has a date was last changed, I went in and edited, let's say function2.c, I went in and edited it and saved it, and now it has a date that's later than my program, and then the make file will remake my program, but it will only have to recompile function2. So this is going to become clearer, I hope, by our example. So here's the example. It's actually this example right here that's in my Notepad++. When you type this in, it's not a C file. It has no extension, or I think there's also a .mak extension, but mine has no extension whatsoever. It's not .text, it's not .c. And this is the simplest form of a make file that we can have. I am going to construct one executable that's called large program. That's the target. Large program depends on having these binary files present, and we have to make those binary files still. So the .o is a binary file. And then if all of these are present and they are up to date, then I'll do this compile command and make large program. But what happens is, if one of these, I've gone in and edited this miscellaneous.c. Maybe I went in and updated miscellaneous.c, which is my main calling program. Let's say I went in and updated this program, then now it has a date that's later. And so I run this makefile, which I'll show you how to run in a moment, and it says, oh, miscellaneous.c is newer than large program. Therefore, I need to compile miscellaneous.c and make the object code. So this object code for miscellaneous depends on the source code, the C code, and if this C code is a more current date, then I have to go ahead and make the object code. And only these parts of the program that are needing to be updated will get updated and recompiled. So so anyway, how do I run that? Let's just show you. So I have my makefile right here. I have a file called writemymessage.c. Let's just update it. This is my message. Save that. Here's my main calling program, miscellaneous.c, running. Let's just update one of those printf statements. Save it. Okay. My header. Nothing really to change in my header. We won't change it right now. Oh, let's change it. There, I changed it. Changed the value of pi. So all of these three files are new. This is the make file. If I go and look at my console window, command prompt, I see miscellaneous.c, my header.h, writemymessage.c, and I have a thing called a makefile right here. And these other ones, makefile2 and makefilegood, are just other things that I'm going to show you later in this video. But you have to call the file a makefile. And when you call the file a makefile, then you can run it by just typing make. And that's what I'm going to do. Make. And so make is going to compile the code. So let's do it. So you can see what it did. It compiled the miscellaneous.c, it compiled this, it compiled that, and then it put it all together and compiled one large program. And I can run one large program. I got an error message. What did I do? It's not recognized as the name of a command. Okay, maybe I just have a typo. Oh, yes it is. It's just a misspelling. So there it ran. So it compiled it into one large executable. And if I ls right now, I do have a large program.exe, and miscellaneous.c got made into miscellaneous.o. That's the binary file. Writemymessage.c got made into writemymessage.o. That's the binary file. And a really interesting thing that took me a bit to figure out is that myheader.h didn't get made into myheader.o. Myheader.h got made into something with a .gch extension on the end. And it turns out header files get made into binary with this extension. So that was a little bit of a discovery for me. So that means that I didn't exactly write my makefile correctly. So this one should be .h.gch, and my header.h.gch depends on my header.h. So that should be fine. Let's save that for a moment. Rerun my makefile. And it said large program is up to date. Why did it say large program is up to date? Because I didn't change any of the dependencies. I didn't change, or the prerequisites they're also called. I didn't change miscellaneous.c, I didn't change my header.h, and I didn't change write my message.c. So let's see what happens if I update just one of these constituents. Let's update, I don't care, let's update miscellaneous.c. I'll say running again. Save that file. And now the nice thing is I don't have to type in a big ugly compile command and compile everything all over again. I can just type make. And so now what happened? It ran make, and miscellaneous.c had to be recompiled into object code, but the other ones did not. And then of course the final big executable gets reassembled here. So and now if I do make again, it'll say everything is up to date. So as you see, then only portions of the code that get changed have to get recompiled, and it's also really convenient just to keep writing make. So that makes it easy. So this make file that we have right here is actually a make file in its very, very simplest of forms. It's very specific to the program I'm trying to construct. Please note also that all the files have to be in the same directory for this to work. And another really important thing right here is this is not spaces. This little indent right here must be a tab. If you put 5 spaces there, it will not work. It must absolutely be a tab. So this is the absolute simplest form of a make file. Make files can get rather complex. Let's discuss the simplest one a little bit more, and then I'll show you how some of the complexities that can get into it and some of the ways also to genericize the make file. So the object codes are the .o. They're bound together by a linker usually, which is invoked through our compiler, the GCC. So you always you start with a source code .c, for example, and then you make the object code out of it, and then the object code gets linked and it makes the executable. All the pieces of object code get linked together and it makes the executable. I do note here that commands, these are the command lines right here, must begin with a tab, and these dependencies or the prerequisites must exist before the target, which is large program, can be made. If these dependencies don't exist, then the program goes down here and makes it. Kind of actually runs backwards in a way from the way it's written. So here I do note that it kind of works backwards, like you run the make file and it goes and it looks at all of these things first. The dot sees the source codes and sees if they're up to date. It checks that first, and then if they're not up to date, it'll make the object code, and then finally it makes the executable. So it's a little bit backwards because it looks like I'm making the whole executable first, but I'm really not. I'm kind of running it backwards. It's kind of doing these checks down here first before it makes the large executable. So these are your source files right here. You have to make the object code. I originally wrote it with a .o for my header, but it's really a .h.gch, which we fixed that, and then I make my large program that's the executable. So my make file works really nice for one computer and one program that you are kind of to create, but you can actually make them more universal. And maybe you have seen, especially if you're a Linux user, you've probably seen make files that have been written more universally. That is a whole other half a semester to learn all about what make files do. They're not just applicable to C programs, they're also applicable to Java and C++ and zip files, and they can do lots and lots and lots of things. So here is a book. It's a free open source book if you wanted to go get it, that talks a lot more about making make files. I think it's a difficult book because it mixes it up whether you're talking about C code or Java or whatever in their examples. But it is a free open source book if you wanted to become an expert at make files. And there's the link right there. So I said that this was the simplest of the makefiles. Note that once again it has no extension. You can put comments in the file. The targets automatically, it recognizes it somehow as a makefile anyway, just by the name of it, because that's a special name, the makefile. So Notepad++ automatically colored it for me. So let me show you some ways to use variables in makefiles. This is just the tip of the iceberg, by the way. So I can declare some variables at the beginning of my makefile. I declared a variable called cc. It's really common to see it called cc. It's saying what my compiler is. My C compiler is GCC. And then when I go down here in the file, everywhere that I had GCC before, I put $(cc). So I've made kind of a variable substitution here. Also, I said my target was large program. That's the executable I want to make. So everywhere in my makefile, I can now substitute this variable $target in parentheses. And so if I wanted to go back and edit my makefile, I can just edit it up at the top with my variable definition. I don't have to edit everything down below. Another thing that you can do, let's look at making the object files from the different pieces of source code. Normally we said gcc-c, and then we had to write out miscellaneous.c over here. You can substitute, do a thing called an automatic variable, which is this $bracket, and it just refers to the file name of the first prerequisite. So $bracket refers to that prerequisite. $bracket refers to that one. So they're kind of shortcuts. You can make all kinds of variable definitions up here. Oh, another thing is I can replace target with $ampersand, and then I wouldn't even have to put the word target right here. And so it can make the file look more and more cryptic, but it can also make it more and more flexible if you're going to be compiling lots of programs. So let me see here. I think I have an example. So there's my improved makefile where I've used some variables at the top. I could have another one called dependencies, and I could make variables for the dependencies over here. So you can do a lot with makefiles if you want to spend the time to learn some of the notation and genericize it. You can even get it to the point where everything here is a variable, and when you say make, you say make my program, and it automatically knows what to do. So there's a lot can be done with makefiles. So here's my new makefile. Let's go ahead and mess around with one of my programs. Let's mess around with miscellaneous. Running finished. Let's say finished again. So I had to update something. Save that. Okay, so now if I run make, and the makefile that I'm going to run is this makefile with some of my variables and shortcuts defined. So let's just check real quick. Yes, so I'm going to run make again, and then it will run that file called makefile. And sure enough, it said that I had to update, I had to recompile miscellaneous.c, which was the file that I changed, and it recompiled the program for me. So that's nice. So let's talk about a little bit more of what you can do when you're dealing with large programs. So when you're dealing with large programs, you might have a definition, like we had a definition of pi, but maybe you have a variable that you defined that's not a constant, so a variable that could change its value per se. But you want to be able to define it in one of your source files, and then your main program can use it when it wants to. So you can do this by declaring the variable as external to the current source file that you're using, and we'll use the extern keyword to show that. So let me show you what I mean. So here's my file that was called write my message. So it doesn't have a main, right? It just has a function definition in it, and it actually includes standard I/O too. And so I added this line of code to it. Just looks like a variable declaration, right? Double inches to millimeters is 2.54 because it's 2.54. That should say centimeters, but it's 2.54 centimeters per inch. So I did looks like a normal variable declaration and definition here, and then in my write my message function, I use it, inches to millimeters equals, and I just put out the values. So then my main program that's going to use it, see, I'm going to say printf 5 inches equals how many millimeters, and then I'm going to use that inch to millimeter thing, which is defined in a different file. But to be able to use inches to millimeters up front, I have to declare it as an external variable that I want to use. So now when this program is compiled, it says there's an external variable, which is a double, called inches to millimeters that I want to use. And then my other program, my other source code, defined what that value was. And so that's how you use the extern command. But this one didn't change in this example. So let me show you that example. I'm actually going to fix it up to do it that way, and then you'll see one of the advantages of using makefiles. So this program isn't going to change. Miscellaneous.c is going to change because I am going to put an extern statement in it. So there I said I want to use an external variable that's a double called inches to millimeters, and then I want to also use it in a calculation in this main calling program. This is my main calling program. So it's not really, it's actually 2.5 centimeters per inch, and I wrote millimeters, but that's okay. You get the idea. So now my main function wants to use that variable that's defined in another file. Let's make sure I have it defined in another file. It is defined over here. Double inches to millimeters is 2.54. Why don't I fix everything up and say it's inches to centimeters, inches to centimeters, inches to centimeters. Fix it up so I'm proper. Save that file. Go over to miscellaneous.c. Fix this up too. Save that file. And now I have these 3 files. My header, same function prototype is declared there. Miscellaneous.c, which is my main calling program, which has changed. And then write my message, which I also changed here. And I want to compile these 3 programs together into one executable called large program. So I wrote a nice make file that will do that, and I don't have to write a big ugly compile command. And so there it recompiled miscellaneous.c, and it recompiled write my message. Let's just run it and see that it actually works. Sometimes you can have a program that you compiled it, but it really doesn't do what you want it to do. And so running, this is my message. Inches to centimeters is 2.54. Conversion factor, value of pi is that, and 5 inches equals 12.7 centimeters. And I finished again! Yay! So the one more preprocessor directive that we're going to talk about is the one called macros, writing a macro. And we didn't go over it. It was in chapter 4 in your book, section 4.9. It's one of those optional sections about macros. But since we're talking about preprocessor directives, let's go ahead and include macros. So you're already used to seeing this define directive, which is actually a substitution. It's not really a variable. And we often define array sizes, for example, in bigger programs. So you're already used to that define statement, but I'm going to show you how it's not really a variable. It's actually a substitution. So it looks like a variable, but it's not. So when I do this printf statement, the value of pi is, and then I put pi there, the code literally substitutes 3.14159 right here in this place, in this line of code. It does not go to a memory location with the identifier of pi and pull out this value and then put it in here. It literally substitutes anywhere that pi is written. It literally just substitutes 3.14 blah 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 blah. So that doesn't even have a data type defined there because it's not a variable. So there is another kind of define that we can do. It looks kind of like a function, and that's called a macro. And this is, like I said, it's actually in chapter 4 in your book. So, but for completeness and preprocessor directives, let's talk about macros. So, like I said, it looks like a function. It generally has this form. You say define, you give it a name, you give it some parameters, and then what you're going to do, what the substitution is actually going to be. So let me show you what I mean actually instead. So I'll go back to the examples that I've been using. This is the miscellaneous.c source code, which has write my message and has my header.h associated with it to make one large program. And I did this additional define up here. I defined this conversion formula, degrees c. That's looks like it's a function of x, right? That's the parameter. And this is what's going to get substituted. So now when I go down, say, to this printf statement down below, I say printf 70 degrees f equals something c, and then I'm not calling a function, but this place that says degree c parentheses 70, that part, it's like it gets scratched out, and literally this gets written into its place. And then it does the calculation. So I changed one of my source codes, but I can just run make and recompile it, and it's, yes, I changed miscellaneous.c, so it recompiled there and made my large program once again with all its other dependencies. And sure enough, 70 degrees c equals 70 degrees f equals 21.1 degrees c. So it works, and it's like a function, but there are a few catches because it's not a function. This is exactly the same as saying, let me just delete that out and put this in right here and put a 70 in where x is. So that's actually literally what will happen when the code runs. It is not a go call a function that I can pass different parameters to. This little piece of code is literally substituted in there. And let's just make sure that runs. Make is so nice. Yes, miscellaneous was changed. And sure enough, it runs. So the other important thing is that you have to put these parentheses around the x everywhere that it occurs, and you also have to have these outside parentheses on the very outside of it. So otherwise it doesn't work right. Looks like a function, it's really not a function. And you can get in trouble if you're not careful. I could find a good example of that, but you can get in trouble if you're not careful. Like if you try to do something function-esque in this argument here, it will not work because of the substitution that's occurring in there. So that's what a macro is, and macros are also useful as we write these larger programs. And I think I'm at 45 minutes just about, which is always where I like to cut it off. So I'll give you a homework related to these concepts. It won't have a lot of programming in it. Matter of fact, I'll probably give you the programs and let you figure out how to compile it all together. That's kind of my plan right now. I don't want to get a lot of homework. I want you to go back and review and study for finals. The next YouTube that I'll do is probably a look at an introduction to C++, and also an introduction, I think, to GUI-based programming, which would, any follow-on course to this one that you would take, you would learn to make the GUIs instead, the little pop-ups that that are associated with running a program. Okay, that's all for today.